porous polymer materials, structure, fabrication strategies, and multifunctional applications. Porous organic polymers represent a versatile class of materials that integrate the structural advantages of porous architectures with the chemical and mechanical tunability of polymer systems. Their low density, high surface area, controllable pore morphology, and adaptable surface chemistry enable broad applicability across environmental, energy, and biomedical domains. This video report provides a comprehensive and descriptive overview of porous organic polymer structures, fabrication methodologies, and emerging applications. Structural characteristics are discussed in terms of pore size, connectivity, and polymer skeleton architecture. Major fabrication strategies, including electrospinning, phase separation, gas foaming, freeze-drying, breath figures, and templating, are critically examined with respect to their underlying principles and resulting morphologies. The relationships between pore structure and functional performance are highlighted across diverse applications such as sensing, thermal management, electromagnetic shielding, separation technologies, and biomedical systems. Finally, current challenges and future research directions are discussed to guide the rational design of next-generation porous polymer materials. Porous polymers have attracted significant attention as a unique class of materials that combine the inherent advantages of polymeric systems with engineered porous architectures. The introduction of pores into a polymer matrix generates a multi-phase structure consisting of solid polymer frameworks and gaseous domains, which profoundly alters the material's physical properties. These structural modifications led to reduced density, increased specific surface area, and enhanced interconnectivity, all of which are critical for applications involving mass transport, energy dissipation, and interfacial interactions. In addition to structural tunability, porous polymers benefit from the intrinsic characteristics of polymeric materials, including flexibility, chemical resistance, low density, and ease of processing. A wide range of polymer systems, from commodity plastics to high-performance engineering polymers and biopolymers, can be utilized to fabricate porous architectures. This diversity enables tailored material design for specific applications. Furthermore, the incorporation of functional fillers such as carbon nanotubes, graphene, metallic nanoparticles, and metal oxides significantly enhances the mechanical, electrical, and thermal properties of porous polymer composites. The performance of porous polymers is governed by a combination of pore structure, polymer chemistry, and composite design. Among these, pore architecture, encompassing size, distribution, connectivity, and porosity, plays a dominant role in determining material behavior. At the same time, the chemical composition of the polymer skeleton and the functionality of pore surfaces influence interfacial interactions and physiochemical properties. Together, these factors enable porous polymers to serve as multifunctional platforms for addressing challenges in energy, environment, and healthcare. Structural characteristics of porous polymers. The structural diversity of porous polymers arises from variations in pore size, connectivity, distribution, and the architecture of the polymer skeleton. Pore size is commonly classified according to established conventions into micropores, mesopores, and macropores. However, in many polymer systems, larger pores extending into the micron and millimeter scales are frequently observed. These different pore regimes contribute distinct functionalities. Nanoscale pores, including micropores and mesopores, are primarily responsible for generating high specific surface areas, which are advantageous for adsorption, catalysis, and molecular separation. In contrast, larger pores facilitate fluid transport by reducing diffusion resistance and enhancing permeability. In practical systems, hierarchical pore structures that combine multiple size regimes are often employed to achieve a balance between surface area and transport efficiency. Such structures are particularly effective in applications requiring both rapid mass transfer and high interaction with target species. The relationship between pore size and permeability can be understood through classical transport models, which indicate that larger pores significantly enhance fluid flow, while smaller pores contribute to selectivity and surface-driven phenomena. Pore connectivity is another critical structural parameter. Open pores, including through pores and blind pores, enable the transport of gases and liquids and are essential for applications such as filtration, sensing, and catalysis. Through pores provide continuous pathways for mass transfer, whereas blind pores contribute to localized interactions and surface functionality. Closed pores, on the other hand, are isolated cavities that do not contribute to transport but play an important role in mechanical resilience, thermal insulation, and buoyancy. The presence of closed pores can significantly enhance the compressive recovery and dimensional stability of materials. Porosity, defined as the volume fraction of void space, has a profound influence on mechanical and thermal properties. As porosity increases, the density and elastic modulus of the material decrease substantially, leading to highly compressible and deformable structures. This characteristic is particularly advantageous in applications such as flexible sensors and wearable electronics. Additionally, increased porosity generally results in reduced thermal conductivity due to the presence of insulating gas phases and increased interfacial scattering. The architecture of the polymer skeleton further contributes to the diversity of porous structures. Continuous frameworks are typically formed through subtractive or templating processes, resulting in well-defined pore geometries such as spherical, cellular, or network-like structures. Alternatively, porous materials can be constructed from assemblies of particles or fibers. Particle-based structures often arise from phase separation or crystallization processes, while fibrous networks are commonly produced through spinning techniques. Fibrous porous polymers exhibit high interconnectivity and flexibility, making them particularly suitable for applications in wearable devices and filtration systems. In addition, hollow and coarse shell structures are frequently employed to enhance functionality in applications such as catalysis, thermal insulation, and controlled release systems. Surface chemistry also plays a crucial role in determining the performance of porous polymers. The presence of functional groups on pore surfaces enables a wide range of chemical modifications, allowing the introduction of specific interactions such as ion exchange, adsorption, or catalytic activity. These modifications can be achieved either through the incorporation of functional monomers during synthesis or via post-synthetic treatments. As a result, porous polymers can be tailored to exhibit highly specific and tunable physiochemical properties. Fabrication techniques of porous polymers. The fabrication of porous polymers relies on the inherent processability of polymeric materials, which can be dissolved, melted, or mechanically structured. A variety of techniques have been developed to control pore formation across multiple length scales, each offering distinct advantages and limitations. Electrospinning is a widely used technique for producing fibrous porous polymers with high surface area and interconnected pore networks. When the polymer is poorly soluble, such as polypropylene, PP, polyethylene, PE, and polyvinyl chloride, PVC, or requires a toxic solvent, melt electrospinning, a technique to produce fibers by using polymer melts, can be adopted instead of solution electrospinning, offering a promising supplemental method for producing fiber-based materials. In this process, a polymer solution or melt is subjected to a strong electric field, resulting in the formation of ultrafine fibers that accumulate into a porous membrane. The morphology and porosity of the resulting structure can be precisely controlled by adjusting parameters such as solution composition, applied voltage, and environmental conditions. Electrospun materials are particularly attractive for applications in filtration, sensing, and biomedical devices, although challenges remain in scaling up production and ensuring mechanical robustness. The breath figures method represents a self-assembly approach in which water droplets condense on the surface of an evaporating polymer solution, forming ordered arrays that template the pore structure. This technique enables the fabrication of highly ordered porous films without the need for external templates. However, the process is sensitive to environmental conditions such as humidity and temperature, which can limit reproducibility and scalability. Gas foaming is an industrially relevant method that involves the introduction of a blowing agent into a polymer matrix, followed by nucleation and growth of gas bubbles to form a porous structure. This approach is particularly effective for producing materials with extremely high porosity and low density. The resulting foams can exhibit either open or closed pore structures, depending on processing conditions. Gas foaming is widely used in the production of polymer foams for insulation, cushioning, and structural applications. Phase separation techniques, including non-solvent-induced phase separation and thermally induced phase separation, are among the most versatile methods for fabricating porous polymers. The phase separation method, introduced by Loeb and Sauer-Arajan in 1963, has been widely studied in the fabrication of porous polymers owing to adaptable production scales and cost-effectiveness. These processes rely on the thermodynamic instability of polymer solutions, leading to the formation of polymer-rich and polymer-pore phases. Removal of the latter results in the formation of pores. The morphology of the porous structure can be tuned by controlling parameters such as polymer concentration, temperature, and solvent composition. Phase separation is extensively used in membrane fabrication due to its adaptability and cost-effectiveness. Freeze drying, or ice templating, is a technique that exploits the crystallization of a solvent, typically water, to create a templated porous structure. During freezing, solvent crystals grow and exclude the polymer phase, which subsequently forms the solid framework. Sublimation of the frozen solvent leaves behind a porous structure that often exhibits directional alignment. This method is particularly useful for creating biomimetic architectures and is widely applied in tissue engineering and thermal insulation. Template-assisted methods provide a powerful approach for achieving precise control over pore size, shape, and distribution. In these techniques, sacrificial templates are incorporated into a polymer matrix and subsequently removed to create pores. Templates can be rigid materials such as silica particles, soft structures such as micelles, or even self-sacrificial components that participate in the formation of the polymer network. While templating offers high structural precision, it often involves additional processing steps for template removal. Overall, each fabrication method offers distinct advantages in terms of structural control, scalability, and environmental impact. In many cases, hybrid approaches that combine multiple techniques are employed to achieve hierarchical and multifunctional porous structures. Applications of porous polymers. The applications of porous polymers are intrinsically linked to their structural characteristics, particularly pore size, connectivity, and porosity. In flexible pressure sensors, the high porosity of the sensing layer results in a low elastic modulus, enabling significant deformation under applied pressure. This deformation amplifies the sensing signal, leading to enhanced sensitivity and performance in wearable and electronic skin devices. In thermal management applications, porous polymers function as effective insulators due to the presence of gas-filled pores and the increased scattering of heat carriers at solid-gas interfaces. Nanoscale pores are particularly effective in reducing thermal conductivity, while anisotropic and aligned pore structures can further enhance thermal regulation by manipulating heat flow and radiation. Porous polymers also exhibit strong potential in electromagnetic shielding and acoustic absorption. The presence of multiple interfaces within the porous structure promotes reflection, scattering, and absorption of electromagnetic and acoustic waves. When combined with conductive fillers, porous polymer composites can achieve high shielding effectiveness while maintaining low weight and flexibility. In separation and purification processes, the interconnected pore network facilitates efficient mass transport, while the surface chemistry of the pores enables selective adsorption of target species. Hierarchical pore structures are especially advantageous in achieving high permeability and selectivity simultaneously, making porous polymers suitable for applications such as air filtration, water treatment, and ion separation. The ability of porous polymers to host and stabilize active components is also critical in applications such as catalysis and energy storage. The high surface area and interconnected pathways enable efficient transport of reactants and products, enhancing overall performance. Similarly, in biomedical applications, porous polymers serve as scaffolds for tissue engineering, providing a supportive environment for cell growth and nutrient transport. They are also widely used in drug delivery systems, where the pore structure governs the loading capacity and release kinetics of therapeutic agents. Challenges and future perspectives. Despite significant advancements, several challenges remain in the development of porous polymers. Achieving precise control over pore size and distribution at multiple length scales remains a critical objective, particularly for applications requiring high selectivity and efficiency. Balancing mechanical strength with high porosity is another key challenge, as increased porosity often leads to reduced structural integrity. Environmental concerns associated with solvent-based processing methods also necessitate the development of more sustainable fabrication approaches. Additionally, the scalability of advanced fabrication techniques, particularly those capable of producing nanoscale features, remains a limitation for industrial applications. Future research is expected to focus on the integration of porous polymers with emerging technologies such as additive manufacturing, enabling the design of complex and hierarchical structures with unprecedented precision. The development of smart and responsive porous polymers, capable of adapting to external stimuli, represents another promising direction. Furthermore, the use of bio-based and recyclable materials will play an increasingly important role in addressing sustainability challenges. In conclusions, porous polymers constitute a highly adaptable and multifunctional class of materials that combine structural tunability with chemical versatility. Their performance is governed by complex interactions between pore architecture, polymer composition, and fabrication technique. Through continued advancements in material design and processing technologies, porous polymers are poised to play a critical role in addressing global challenges in energy, environment, and healthcare.